AP Cam, here is a little bit of your gases multiple choice review. I get this a little bit organized here if you need some help on this stuff. All right. First question. Distribution speeds of H2 molecules at 273 Kelvin when atmosphere is shown in the diagram above, which shows the speed of HE atoms under the same conditions of temperature and pressure. So H2 compared to HE, mass of 2, HE mass of 4, H2 is going to be a little bit faster. So if you look at this, okay, it's hard to read what it says here. This is the relative number of particles. This is the speed. So faster speed, slower speed. Okay, a high curve does not mean a faster speed. It just means more particles at that speed. Okay, so if we're looking at these, this one right here shows this gas has a lower speed on average than this gas. And just look at the middle of the curve, middle of the curve, middle of the curve. So this is actually slower than this one. I didn't mean to do that. I went through there. And it is saying that HE is the dash one, so actually that'd be the correct answer. If we look at these other ones here, the dash one has a higher average speed than the other one. This one is just saying there's more particles of one than the other as you're going through. All right. Increasing the external pressure on a gas in a flexible container, so like a syringe, like pushing that syringe in, does what to the kinetic energy? Does nothing to the kinetic energy. Kinetic energy is only affected by temperature. Increases the influence of intermolecular attractions. I'm not sure if you know what that even is yet, intermolecular attractions, but molecules have some attraction for each other. The closer they are, the more attraction there is. So increasing the pressure would increase those. Not too concerned about that at this point in time. Will be later in the year. All right. You have air in this cylinder with a movable piston, so they can move this up and down. So it's going from 2 liters to 5 liters from there. So P1 in the first one, volumes increased to 5 liters as temperature is held constant, so temperature is not changing. And it wants to know what happens to kinetic energy. Well, kinetic energy is only affected by temperature. So there's no change in temperature. All we're doing is changing the volume of air. So the kinetic energy would stay the same. Letter C there. All right. Number 4 here, you got 4 liters of gas, 6 liters of another gas, and 10 liters of another gas, all at 0 degrees, 1 atmosphere, are pumped into an 8-liter container. What's the final pressure going to be? So each of these is at 1 atmosphere of pressure when they're put in there. So if you would take 4 liters of gas, put into an 8-liter container, it's going to be twice as much space. Its pressure is going to go down by half as much. All you got to do is add up the liters here. So we have 4 liters plus 6 liters plus 10 liters. You have 20 liters of gas. If you would take 20 liters of gas at 1 atmosphere of pressure and put it into a container half the size, you'd have to double the pressure. Well, in this case, we're going from a 20-liter total, going from 20 liters total into an 8-liter container. So you'd have to more than double the pressure right there. You could take 20 divided by 8, which would be 2.5. Samples of 2 different non-reactive gases, they don't react with each other. Light's bad, sorry. Are placed in a closed, rigid container, so it's not flexible, at 273 degrees Kelvin, as shown below. Sample consists of, you ask about gases. So this is a diatomic element like O2. So that's O2, 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 O2. This is a monatomic element. So it is 2 different elements. Okay, this is not considered a compound. It is a diatomic element. So it's 2 different elements. Under what conditions does SF6 gas behave least like an ideal gas? Least like an ideal gas. So remember, at really cold temperatures and really high pressures, gases do not follow the PV-nRT. They don't follow the ideal gas law very well. Things just don't work out very well. So we're looking for cold temperatures and high pressures. Well, the highest pressure is 125 atmospheres. There's not much difference between 25 degrees Celsius, 50 degrees Celsius. So it would be letter C there. Here's an old question. This is a dilution problem. What volume of water must be added in order to dilute 40 milliliters of 9 molar HCl to a concentration of 6 molar? So if we got 40 milliliters of 9 molar, if we add a little bit of water to this, the concentration will eventually go down to 6 molar. We can MVMV this. So if we go 40 times 9 equals 6 times V. So 4 times 9 is 360, divided by 6 is 60. 60 milliliters. That is not going to be the answer, though. Okay, so you can dilute 40 milliliters of 9 molar HCl. You can dilute it to 60 milliliters of 6 molar. That means you had to add 20 milliliters of water into this solution. So if we add 20 milliliters of water into this, we'll make 60 milliliters of that. So you would actually have to add 20 milliliters of water in to get to there. Number 8, 10-liter cylinder has 10 grams, 40 grams, 64 grams. Total pressure in the cylinder in atmospheres at 27 degrees Celsius. Well, let's figure out how many moles we have of these things. So NO would have a mass of 16 and 14 have 30 grams. So divided by 30 is about 0.33 moles. 40 grams of argon, well, that is what argon is for a mass. That is 1 mole. And 64 grams of O2 is 32 grams per mole, so that'd be 2 moles. So we have 3.33 moles of gas. Well, we could PV-nRT this. And figure out what our pressure is. So P times 10 equals 3.33 times 0.0821 times 27 degrees Celsius is 300 degrees Kelvin. Well, I can probably figure this out in my head. 300 times 3.33 is about 999. It's almost 1,000. 1,000 times this, when the decimal in 3 places, would be about 82.1 equals P times 10. So divide by 10, about 8 atmospheres pressure. By the way, up there, the gas that's the most number of moles would be causing the most amount of pressure, obviously. Using this reaction between this and this, reaction between NO molecules, those are NO molecules, and O2 molecules, is making NO2. Pressure is recorded before and after the reaction. What predicts the change in pressure as the reaction goes to completion at constant temperature? Well, same temperature, same size container, so we just need to know how many moles of gas there are. More moles of gas, more pressure. In this first one, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 moles of gas. At the end of the reaction, we have 1, 2, 3, 4, 5, 6, 7, 8 moles of gas. Since we are decreasing moles of gas in the same size container at the same temperature, we're going to decrease the pressure. So there'd be a decrease in pressure because there are fewer molecules of product than reactants. That's letter B. All right. Given this information, which behaves the most like an ideal gas? So we want just kind of normal temperatures and normal pressures a little bit. Higher pressures we do not want. So if we look at this, you're at 20 atmospheres, 20 atmospheres, 20 atmospheres, 20 atmospheres. Those are all pretty high pressures. So H2 would probably behave the most like an ideal gas. and which would have the lowest root mean square speed. Hang on a second. So lowest root mean square speed, which one's going to be moving the slowest? Temperatures are basically 200, 200, 200, 200, 300. So that's going to be moving faster. We can eliminate that one. The slowest one then would be the one that has the most mass. So between H2, not that one. O2 has mass of 32. SO would be about 48. And H3 about 17. So SO would have the slowest speed. So 11 would be C. And that's all we got for that one. All right. Addition of sulfurous acid, a weak acid, to barium hydroxide, a strong base, results in the formation of precipitate. What is the net ionic equation? So if it is a weak acid, we need the whole thing, H2SO3. So we can eliminate A and C because they don't have the whole thing there. All we need for a strong base, is the OH negative. Okay, just the OH negative to be in there. So with the barium ions on here, these, by the way, it's hard to read this. Sorry, those are your arrows. It's going to make a precipitate, it says. So the precipitate there has to be barium sulfate. So we need to have barium sulfate as a precipitate, which eliminates this one because it has the barium split up into there. We eliminated C because the sulfurous acid was split up. So we are left with two choices, B or E. Well, barium hydroxide would be aqueous. It's split apart into ions, making solid of that. So there's your net ionic equation. Old stuff there. All right, a couple left here. Two different non-reactive gases placed in a container. If each molecular atom shown below represents 0.1 mole, total pressure in the container is 1,200 millimeters of mercury. What is the partial pressure of triangle? Well, you have two triangles out of 1, 2, 3, 4, 5, 6, 7, 8 out of 8. So 1/4 of the pressure, 2/8 of the pressure, 1/4 of the pressure is triangle. So 1/4 of 1,200. 1/4 times 1,200 would be about 300 millimeters of mercury. So the triangles are causing 300 millimeters of mercury pressure. The other 900 is the two circles. 14, increasing the temperature of an ideal gas from 50 to 200, it causes the average kinetic energy to increase by how much? Be careful here. Looks like it'd go up 4 times. Okay, but it has to be in Kelvin. So if you put these in Kelvin, put these temperatures in Kelvin. So 273 plus 50 is about 323, going up to 573. So we're not quite doubling. Should be a little bit less than 2. So increases by less than a factor of 2. And last one here, I think, shows a mixture of two gases, two rigid containers. The gases are identified in the key on the right. Assume that no reaction takes place between the gases. All gases behave ideally. Total pressure in figure 1 is 5 atmospheres. Total pressure in figure 2 is greater than 5 atmospheres, which best explains the reason for the increase in total pressure of the system. Well, we have, let's count the number of molecules. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 moles, we'll say, of gas. And over here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 moles of gas over here. So there's an increase in moles of gas. Let's talk a little bit more about this. If this is 5 atmospheres at 15 moles, 18 moles would be, the same ratio would be 6 atmospheres of pressure. The partial pressure of the gases, as long as the number of molecules stay the same of each gas, the partial pressure of each gas would stay the same. So if we still have, let's look at this gas. 1, 2, 3, 4, 5, 6 of those. 1, 2, 3, 4, 5, 6 of those. Since those are the same number, you still have the same partial pressure of those. There are a few more questions here. We'll do one more here. Given this reaction, there's your arrow right there. You have 4 atmospheres of NH3, 4 atmospheres of that. Reaction 25 degrees Celsius 10 liter container, and the products are kept in the same 10 liter container at the same temperature. What would be the pressure in the container after the reaction? Well, since we're going from 2 moles of gas to 4 moles of gas, okay, 2 moles to 4 moles. This was 4 atmospheres, twice as many moles. That's going to be twice as many atmospheres, 8 atmospheres. Have a good day.